All right, y'all. Last video, intuition builders and wrap up. Here we are. So I want to give two intuition builders and a table to kind of hopefully solidify some of the things we've talked about. The first intuition builder is just the angular momentum of the planets around the sun with some extra added bonuses. So what I'm going to do is I'm going to calculate the moment of inertia and angular velocity of all the planets, assuming circular orbits, which is a bit of a big assumption, but we're just going to take it and run with it. And then what I'm going to do is figure out the total angular momentum of the solar system. I actually don't know what it is, so here we go. Let's see. Okay, so what first thing I'm going to do is I'm going to find all the masses of the planets and write them down. So edit this out. All right, so there's all the masses. In order to figure out the moment of inertia for each of these, I'm going to need also the distances, so how far away they are from the pivot point, namely the sun, the point they're all rotating around. So let's find those radii. All right, done. So now I have the radii, the average radius, and the mass of each of these planets. So let's draw a little diagram here to demonstrate what I'm going to be doing next. I'm going to be calculating the moment of inertia for each of these. And remember, I'm trying to get at the moment of inertia because the angular momentum is I times omega. So I need the I in order to calculate that angular momentum. So all of the planets are rotating in the same direction around the sun. That's actually going to be important later. They're all rotating around the sun, and I'm going to exaggerate a little bit here. Let's pretend that there's only 4 just for convenience. So what I've got is I've got these vectors, these r, which are all some length. That's the average distance, say, the distance from the planet to the Earth, the planet to the sun. Here are my r's. And each of them have a mass. M1, M2, M3, etc. M2, M3, M4. Oops, and let's go and draw in our letters for R. So here's R1, R2, R3, etc., R4. So we do that for all the planets. That's going to tell us the moment of inertia of each planet around the sun. So let's do that next. All right, so for each of those, I multiplied the mass times the radius squared. That spat me out each of these moments of inertia. From here, to find the total angular momentum of the solar system, what I'll need to do is find the angular velocity, omega. So recall that the angular momentum, L, is I times omega for any given object in our system. So each of these planets has its own angular momentum, and the total angular momentum of all the planets is just the sum of each of those individual angular momenta. So I mentioned a second ago that it's kind of important that each of them are traveling in the same direction. So say that in my reference frame I'm viewing the solar system in such a way that they're all rotating clockwise. In that case, all of my angular momentum vectors are going to be pointing down into the page. I shouldn't say down doesn't make sense. Into the page for L. So each of them has a angular momentum pointing into the page, which means the total angular momentum will just add. It'll all stack into the page. However, we'll see in a minute that if I change the direction of one of the angular momentas, I have to think about that a little bit. It's going to subtract instead of add. Okay, so what I want to do now is I'm going to take the periods of each of the planets. Let's go ahead and poof those into existence. All right, there are all the periods in units of 10 to the 6th seconds. So the period is how long it takes to complete one cycle. So there are 2 pi radians in a single cycle. So what I can do to find my omega, at least the magnitude of it, magnitude of omega is 2 pi radians per time, per cycle, per period. There we go. So I can find the magnitude of all my omegas just by dividing 2 pi by whatever I found for the period. Let's poof that into existence. Here we go. Boom. Okay, found my omega. So for each of my angular velocities, I can now compute using the angular velocity of each planet and the moment of inertia of each planet, the contribution to the total angular momentum of each planet, magnitude-wise. So the magnitudes of each individual angular momentum. I'll do that by multiplying I times omega. All right, here goes. All right, there we go. So if you look, the major players are basically Jupiter, Saturn, Uranus, and Neptune. That makes some sense to me because they've got the most mass and they're pretty far away. Jupiter being the biggest player doesn't surprise me too much. It's got a pretty fast rate of rotation compared to the other gas giants. Yeah, so the fact that it's almost 3 times as big as the next biggest uh, tells you something. Jupiter's a big deal. Jupiter contributes to our angular momentum a lot. All right, so there's calculations of the individuals. To find the total angular momentum, I just need to add them. And remember that in reality, this is a vector addition. So I'm adding in a bunch of vectors that are all pointing, again, out of the page. Sorry, into the page. Oh no, I've made a mistake. Yeah, so previously I realize now I said that the angular momentum for each of these was pointing into the page, and then I wrote a dot. It should be into the page with an X. Sorry about that. There's L. My fault. Okay, so since each of them is pointing the same direction, we can just add them together linearly. So let's do that. We'll just add them all up to find the total. L total. So I get something like 3.2 times 10 to the 6th. And then if I compare that with my units up here, okay, cool. So the scaling units here are 10 to the 39th. Okay, so times again 10 to the 39th kilogram meters squared per second. Okay, now you might notice I've dropped the radian. It's because a radian isn't truly a unit. It's not a physical unit. It's kind of just it's just a ratio. It's a ratio between two things in geometry. Don't worry too much about it. Just know that I usually keep the radian in place to remind myself that I'm talking about, for example, an omega or an angle. But radians isn't really a true physical unit. It's not quite like kilogram or mass. It just refers to a ratio between two things. Okay, so that ends up being 32 times 10 to the 45th, whoa, kilogram meter squared per second. Okay, now say that I reversed the orbit of Jupiter. Say that I switched it around. So it's now moving in the opposite direction of the other planets. Let's say that this M3 is Jupiter. And I switch it around, so it's pointing in the opposite direction. Well, now I've got some vectors that are additive with one another into the page. But this one, the one associated with Jupiter, is going to be out of the page. So effectively what that means is all of them add except for the angular momentum of Jupiter, say, and that one will subtract. Minus. Okay, so if I do that same addition, adding them all up and subtracting off the one that's going the opposite direction, Jupiter, as a kind of like vector subtraction, what I get for my total momentum, if I were to spontaneously reverse Jupiter's course, is a total angular momentum magnitude of around 8 times 10 to the 5th times 10 to the 39th kilogram meters squared per second. And it's actually in the opposite direction. So this is 8 times 10 to the 44th kilogram meters squared per second. And it's in the opposite direction. So again, I'm trying to demonstrate here the fact that it's a vector sum. So the fact that, say, Jupiter's trajectory gets switched around means that whereas previously, let's draw in a little plane here, a little planar picture of the planets moving around. Say that they were moving, there we go, something like this. We're looking at kind of like a flat view now of the solar system, watching the solar system move from the side, so to speak, instead of from above in the previous picture. The planets are going around clockwise, let's say, except for Jupiter. And Jupiter is going the opposite direction, counterclockwise. Okay, so these two planets, their angular momentum, according to the sun, is going to point down, according to the right-hand rule. 1, 2. But Jupiter, with its reversed trajectory, has an angular momentum that points up, like through the center of the donut, so to speak. And it's enough that it swaps it around to the other side. Disclaimer, obviously, Jupiter is not orbiting in the opposite direction as the rest of the solar system. This is just a hypothetical. Cool. Okay, the last thing I wanted to leave y'all with is this. Hang on, where is it? This little table, analogs between linear and angular quantities. Actually, I'll full size it for the purpose of the video. There we go, a little bit bigger. So I've got a couple of analogies lined up between linear and angular momentum, and you can also see there some important equations associated with them. So I try to be sure that you're comfortable with each of these equations and understanding each of the individual terms.